Observe carefully. What do you see is the difference between these two images. This is the biggest mistake in valve sizing. Did you observe the difference? In this video, we will learn in the step 1 what is the mistake, and in the step 2 we will learn, especially which is the best part of it, what is the equation to solve this mistake. So without further delay, let's get into it. Is a valve generally, and the valve has a rated CV that we use. So for example, here if we try to find out the rated CV here for a 1-inch valve, we'll get to know that the CV at 100% of the opening is 16.9. So we take the rated CV in calculation, and then we take the graph here where the rated CV has to accommodate the calculated CV between 20 to 80%. But here we are missing a very important step. Now if you notice, any valve is not connected to a line directly. You have these amazing reducers and expanders, and the valve's rated capacity that is available in the catalogs will not include the effects of reducers or expanders. You might think the effect of reducers and expanders is negligible. The answer is no, it has a very huge impact. We will take this understanding from Control Valve Premier, a top-notch book for control valves by Hans D. Baumann. If you look at a valve, let's imagine the CV of the valve to be 100 and the piping geometric factor is called as FP, which is, let us assume here, to be 0.8. Now the resultant CV of this entire system can be called as CR, for example, which will be equal to the CV into the piping geometric factor. So for example, if your valve has a CV of 100 but the FP is 0.8, you will only have the resultant CV of 80 CV. That means a huge difference is lost just because of the piping geometric factor. Let me share with you a pro tip also here. The line sizes for a valve generally is considered to be one size less than the actual line size, or maximum the valve can be half than the line size, but going smaller than that will cause a lot of stress in your line. What we have just learned is the mistake that happens, especially of not considering the piping geometric factor and control valve sizing. Now we look at the equation, which is the most important part. How much time will it take for you to memorize this formula? After watching the video, you will not even have to memorize this formula. In piping geometric factor, there are only two important components to be considered. The first is we need to know about the valve size that we are selecting. So for example, we know for a 2-inch valve size what is going to be the rated CV, that upon your valve size. So if it's a 3-inch valve, then it becomes 3 square. This is just one term to be considered. And the second term, as we already saw, is going to be the piping fittings. So here the piping fittings are to be considered as summation of K. We will look into it. What does this mean? Upon just a constant, which is N2 here, this will remain constant. If you have your valve sizes in inches, it is going to be 890 regardless. And then here you have the equation of 1 plus and the whole raised to minus half. Once you know this, now let's look into what is the summation of K meaning. Here the summation of K plays a very important role in piping geometric factor. So if you see here, these fittings are going to have some resistance. So the resistance coefficient of inlet and the outlet is considered as K1 plus K2. So these are the two resistance coefficients that are going to be applicable, plus there are going to be some Bernoulli forces acting at the inlet side plus at the outlet side. So we are going to term this as KB1 and the other one is going to be termed as KB2. Now these are going to subtract each other. Now let me tell you a very happy news. For majority of your sizing applications, the inlet size is usually going to be equal to the outlet size of your line. That being said, your KB1 will always then be equal to KB2, which is a Bernoulli factor, if you are using a concentric reducer and expander, which is mostly used in 99% of the cases. Once we substitute this, we get to know that KB1 and KB2 will cancel each other out. So we are just left with K1 and K2. Now since the inlet is equal to outlet, the equation basically uses only two factors. The valve size, for example, the valve size here was 3 inches, so 3 square divided by the line size, which is going to be, for example, 6 inch, so 6 square, the whole square, and you have these constants here. So basically this will give you summation of K. Once you get this value, you put it in the main equation. Once you put it in the main equation, you will get to know your FP factor, which is generally going to be in the range of 0.6 to 1. Imagine your piping geometric factor comes to be 0.6. If we have our CV actual of this entire system, which is going to be FP into your CV, your FP value, let us assume it to be 0.6 is what you got, into your CV, even if it is 150, you're only going to get a resultant CV of 90. So did you realize how much big of a difference difference a piping geometric factor can play, but this was just one part of the sizing. How the entire steps of what an engineer must consider when sizing a control valve in a software, this video here will genuinely help you to clear all those doubts. So I'll meet you there.